Hello everyone. Today's lesson is lesson number 3 of the second term. So we're going to learn about gases and gas laws. Okay, let me share with you the notes. Okay, gases and gas laws. So we're going to talk about ideal gases. And we're also going to talk about real gases. Okay, so we have particles in motion, which is called kinetic theory. Kinetic word means motion. It is a Greek word from kinesis, which means motion. So we have 3 phases of matter. We have solid, liquid, and gas. Just like water, we know that water can be in the form of a solid as an ice. It can be in the form of a liquid water, and it can also be in the form of a gas as water vapor. So with particles, for example, in a solid, we know that they're in a constant motion. In liquid also, the particles are in constant motion, even in gases. In liquids, we know that the particles, of course, are moving freely. They're not attached to each other, even though they are attached to each other, but they are free to move. In solid particles, of course, they are attached to each other and they are not free to move. So in gases, particles are far apart from each other and they are free to move. So, for example, particles in a gas, such as ammonia, they spread very quickly through the air, for example, in a room or in a classroom. So this process of spreading the gases, for example, in a room from one position to another position is called diffusion. This occurs also in liquids. For example, when you put a water-based juice in water, I mean, you can see the particles of juice, moving down the water. And you'll see the water changing, a color by taking the color of the juice. Kinetic theory of gases. We know that all matter consists of particles in a constant random motion. In solids, particles are close together and they exhibit vibratory motion. In liquids and gases, particles are further apart and free to move. Particles, of course, can vibrate, they can spin, and they can also move from one place to another. And this is called diffusion. In gases, particles, they are free to move and they have a space, in between. That's why you can be able to compress a gas. Molecules bump into each other and they also collide with the walls of a container. By so doing, they create a pressure that acts in all directions. Molecules in a sample of gas particles all move at different speeds. However, the average speed of the particles remains the same at a certain temperature. And we also know that our average kinetic energy is directly proportional to the temperature. It is the case because the definition of temperature is the average kinetic energy of the object or of the particles. That is the temperature. Particles moving at different speeds, but they have the same average kinetic energy. And kinetic energy is measured by this formula, which is half mv squared. We can see that the particles are moving to the same, to different directions, but they have the same average kinetic energy. Let's consider this example quickly. So here we have in this three different examples. We have matter here, or particles, in a gas form, in a liquid form, and also in a solid form. So now we need to choose the particles that are in the solid form, particles in the liquid form, and particles in the gas form. Okay, let's see. Let's start by choosing the particles in a solid form. So we need to check the particles that are close to each other. You can see these ones, they are very close to each other, which means this is the red one stands for particles in a solid form. Here the particles are in a liquid form. And the last one, the green one, represents the particles in a gas form. You can see they are far apart to each other. So particles in a solid form, of course, they're close together. The red one, liquid, particles are further apart, and particles in a gas form are far apart, which is the last one. Ideal gases. The word ideal means perfect, but we know in nature that there is nothing that is perfect. So an ideal gas is a perfect gas, or an ideal gas is an imaginary gas where the particles are identical in all ways. Particles occupy no volume. They exert no force on each other except during collisions. For example, there is no gravitational force between the particles, and there is no electrostatic force between the particles. They collide with perfectly elastic collisions in which energy is conserved. They obey gas laws under all circumstances. As pressure is increased, the volume approaches zero or decreases to zero volume. So you can see here, this apparatus here, where there is a piston that can be moved up and down. When it is moved up, of course, the volume increases and the particles becomes far apart from each other, which means the pressure decreases. When the piston is moved downwards, it compresses the volume, which means it decreases the volume, and by so doing, the particles becomes closer to each other and the pressure of particles increases. Ideal gases versus real gases. Real gases deviate from the behavior of ideal gases at very low temperatures and also at very high pressures. Most of the time, real gases behave like ideal gases. The real gases that behave closest to the ideal gases are, for example, helium gas and hydrogen gas. Helium gas is denoted by He, and hydrogen gas is denoted by H2. The relationship between the properties of a gas. In order to fully describe and study a gas, we need to consider like some quantities of a gas. So for example, the amount, which can be represented by a mass or by the number of moles. Then the volume, pressure, and the temperature of the gas. To see how these quantities are related to each other, we need to keep two variables constant and then see how one changes as we change the other variable. Gas pressure and volume. Of course, we are surrounded by millions of air particles at all times in the atmosphere. These particles, of course, they exert pressure on us in all directions. The pressure is called the atmospheric pressure. Sometimes we may not notice it because we are used to it. And the amount of this atmospheric pressure is 1 atm, which is 1 atmosphere. This 1 atm is equivalent to 100 kilopascals. So we can use a bicycle pump, for example, to change the volume and the pressure of a gas. When you press it to close or to decrease the volume, the particles becomes close to each other, which means the pressure of the particles increases. So now when we increase the pressure of the particles, of course, the particles, they collide to each other with a high speed. Remember, when we increase the pressure, the particles are very close to each other. So now they collide with each other and collide also with the walls. When we double the pressure, we are also decreasing the volume, which means the volume will be half. If we have the pressure, then the volume is doubled, which means the volume and the pressure when the temperature is constant varies with the same scale factor. You can see in the diagram here we have a apparatus which is called Boyle's law apparatus. The apparatus is used to investigate the relationship between pressure and volume for a fixed number of molecules of a gas at a constant temperature. So this apparatus is named after the scientist here called Robert Boyle, who was an Anglo-Irish chemist and physicist. Boyle's law. So as you can see, this is Boyle's law apparatus. The first arrow here pointing at A, of course, indicates the air that is trapped in tube A. At the bottom there, the arrow pointing at B indicates air which causes an increase in pressure. The pressure on top of them represent a gauge where the arrow on top of there represent a gauge where pressure is measured. Then the arrow here at the bottom at D represent the air that is pumped in. Then the arrow at the bottom here represents the oil reservoir. Okay, now the figures are recorded here in the table. The first column we have the figures of volume. Second column, the pressure that is recorded. Then when we divide the volume by 1, then we get the reciprocal of the volume. When we multiply the pressure and the corresponding volume, then we get the product of the pressure and the volume. Boyle's law. So drawing the graph for those numbers, then we get this graph here. Pressure, of course, we're pumping air in to change the pressure there. Then we got the volume. The shape of the curve reminds one of a hyperbola. If this is the case, the equation will be PV equal to K, which means the product of the pressure and volume remains constant. Then we say pressure is inversely proportional to the volume. As you increase the pressure, the volume decreases, provided that the amount of the gas and the temperature remains constant. As the curve could be something other than a hyperbola, we can check as follows. If PV is constant, then V is equal to 1 over pk. A graph of V versus the reciprocal of pressure will therefore indicate a straight line through the origin, which compares with y equal to mx. As a straight line is obtained, it means that the original graph was a hyperbola. Therefore, PV is equal to K. Remember from mathematics, we get a hyperbola from xy equal to K, where K is constant. So when we sketch now V against the reciprocal of pressure, then we get a straight line like this, where we have 1 over pressure and then we have a volume. The volume of a given mass of gas is inversely proportional to the pressure exerted on it, provided that the temperature is constant. From the definition, the relationship between the pressure and the volume, we get the equation which is derived from this relationship. Since P1 V1 is equal to K, and P2 V2 equal to K, P3 V3 equal to K, P4 V4 equal to K, we saw that from the previous table. Then which means P1 V1 is equal to P2 V2. Then we can also say P initial V initial is equal to P final V final. We call this Boyle's law equation. Note that the quantity of gas should remain the same, which means the amount of the gas should remain the same. The mass or the number of moles of the gas should remain the same. Also, the temperature of the gas should remain the same for the Boyle's law equation to be applicable. Okay, let's consider here the first example. It says if the product of the pressure and volume is constant, what would the unit of measurement for K be? Let's do that together quickly. If PV is equal to K, let's write the units together quickly. So this is example number 1. Okay, 1.1, we say K, we're considering the units. K is the product of PV. Pressure is measured in pascals. And the volume is measured in meter cubed. Pascal is the same as Newton over meter squared because pressure is the same as force divided by the area in which the force is applied. As you can see on top, we have 3, at the bottom we have 2. Then what we are left with is Newton times a meter, and this is the same as a joule, which means the unit of K is a joule. Okay, let's go back to the questions. Second question. It says state Boyle's law. State Boyle's law. That is the second question. Let's write it together quickly. That is number 2. Number 2 is supposed to state Boyle's law in weights. It states that the volume of a given gas with a given mass is inversely proportional to the pressure exerted on the gas provided that the temperature remain the same. Okay, in other words, the volume of a given mass of a gas is inversely proportional to the pressure exerted on it, provided that the temperature of the gas remains constant. Yeah, let's go now to number 3. Question number 3, a gas sample has a volume of 220 milliliter. What is the new volume if the pressure changes from 150 kilopascals to 225 kilopascals? Okay, let's write that quickly together. So we're given V1, which is 220 milliliters. We're also given P1, which is 150 kilopascals. We also have P2, which is 225. The question is to calculate V2, the new volume. Let's do that quickly together. Uh, 3.3. So V1 is given as 220 milliliters. Remember, a milliliter is the same as centimeter cubed. Then P1, the first pressure, is the same as 150 kilopascals. What else is given? We're also given the second pressure, which is the same as 225 kilopascals. So we are required to calculate a V2, which is the second volume. Okay, which formula are we supposed to apply? Of course, we're supposed to apply Boyle's law formula, which is P1 V1 equal to P2 V2. What are we looking for? We're looking for V2. Let's make substitution. Where there is P1, we write the value of P1, which is 150 kilopascals. Where there is V1, we write the value for V1, which is 220 milliliters. Where there is P2, we substitute the value of P2, which is 225 kilopascals. V2 is the unknown that we're looking for. Then what you can do, you can divide both sides by 225 kilopascals to make V2 the subject of the formula. What you do in the right-hand side, you also do in the left-hand side. Then this will cancel. So in the right-hand side, we're left with V2, which is now the subject of the formula. Okay, let's punch a calculator quickly. 150 times 220 divided by 225. What is the answer? 147. 147 milliliter. Remember, a milliliter is the same as a cubic centimeter. So we can also write it as cubic centimeter. Okay, let's go back to our notes. Okay, the volume temperature relationship. Okay, to record the volume of the air column below, we use the mercury because mercury is very sensitive to temperature. So as the temperature rises, so the mercury also there changes, then we can record now the volumes. Temperature increases, so the volume also increases. And we need to study now this relationship between the volume and the temperature. So this is known as Charles' law of volume. Okay, of course, this is named after a Frenchman called Jacques Charles, who was a scientist. Okay, let's consider the sketch there. So as you can see, this dot here represent a drop of mercury. Remember, mercury is very sensitive to temperature. That's why it is used in a thermometer. Then the second arrow there indicates a thermometer, as you can see. Then this one, the third one there indicates the air that is trapped in the tube. And the one at the bottom there represents the ice cube. So the ice cube are used to change the temperature. So we're using the ice cubes there to drop the temperature. Okay, so now we can record the first amount of the volume there is 38, which correspond with -5 degrees in Celsius. When the temperature is 0, the volume is 39. When the temperature is 100, the volume is 53,3. Then we can draw a graph for those values. So we have a temperature that we are adjusting there at the bottom by the number of ice cubes. Then we have the volume there as y-axis. So when the temperature is 0, of course we have a corresponding value then of the volume, which is 39 cubic centimeters. Then when the temperature is 100 degrees, then we have the value of the volume corresponding with 100 degrees, which is 55,3. Then we can sketch. Remember, 0 degrees Celsius corresponds with 273 Kelvin, and 100 degrees Celsius correspond with 373 Kelvin. Because to get Kelvins, we add the Celsius with 273. So we can also sketch this graph in Kelvins, or with the temperature in Kelvins. So that is how we get, or we sketch the graph. Along the y-axis, we have volume. Along the x-axis, we have the temperature. So remember, the first one does not go through the origin. It doesn't pass through the origin. So if we want this graph to pass through the origin, what do? We convert the temperature into Kelvin. So when the temperature is 0 Kelvin, then also the volume is 0. When the temperature is 273 Kelvin, then the volume is 39. When the temperature is 373 Kelvin, then the volume is also the same as the volume that corresponds with 100 degrees Celsius, which is 53,3 cubic centimeters. So we can sketch the same graph. I mean, for pressure, remember when we increase the temperature, pressure also increases with the same scale as the volume, increases. Then we can sketch the graph, which is similar. The graph will be similar to volume temperature graph. It's just that the values of the pressure, of course, are going to be different. Okay, let's consider now the volume temperature relationship and the pressure temperature relationship. The relationship between the volume and the temperature gives us this law. V1 over T1 is equal to V2 over T2, which means the volume is directly proportional to the temperature. And this relationship is called Charles' law. The relationship between the pressure and the temperature will give us P1 over T1 equal to P2 over T2. And this relationship, it is known as Gay-Lussac's law, because it is named after a French chemist and physicist, which is called Joseph Gay-Lussac. Okay, let's consider the second example here. A container of nitrogen gas has a pressure of 200 kilopascals at a temperature of 20 degrees Celsius. So we need to calculate the pressure of the gas when the temperature is raised to 25 degrees Celsius. So which means here we're going to have the first pressure, which is 200 kilopascals. The first temperature is 20 degrees Celsius. The second temperature is 25 degrees Celsius. Okay, we need to calculate the pressure. Let's do that together quickly. Okay, this is example number 2. Example number 2. So let's write the known values. P1 is 200 kilopascals. T1 is 20 degrees Celsius. So now we need to convert, it's always the case, we need to convert this temperature into Kelvin. So we add 20 into 273. How much are we getting here? We get 293 Kelvin. What else is given is the second temperature, T2, which is given in degrees as 25. We need to convert it also into Kelvin, so we add 273. So which gives us 298 Kelvin. Okay. Then let's apply this formula. P1 over T1 is equal to P2 over T2. We're looking for P2, so this is also the same as P2 over T2 is equal to P1 over T1. Now let's substitute the known values. P2 is what we are looking for. Then T2 is 298. Okay, to avoid making mistakes, the best thing here is to substitute the units as well so that you can see how it cancels out. So pressure is 200 kilopascals. That is first pressure. The temperature, T2, okay, so it's T1. T1 is 293. Okay, so we can multiply both sides by 298 to cancel this 298. So how much are we getting for P2? Okay, we get 203,42 kilopascals. And if you write it as a whole number, it's 203 kilopascals. Okay, that is the answer for P2. Okay, let's go back to our notes. Now combining the two laws, Charles' law and Gay-Lussac law, then what do we get? We get P1 V1 over T1 equal to P2 V2 over T2. which means as you increase the temperature, both the volume and the pressure increases. This is known as the general gas equation. Okay, which is used provided that the temperature and pressure are in a standard condition. Okay, the standard condition of pressure is 1 atmosphere, which corresponds with 100 kilopascals. The standard temperature is 0 degrees Celsius, which corresponds with 200, which is also the same as 273 Kelvin. Okay, please at home, don't confuse the standard temperature with a room temperature, which is 25 degrees Celsius. Standard temperature is 0 degrees Celsius. So to convert the temperature from degrees Celsius into Kelvin, we use this formula. Capital letter T stands for Kelvin. T equal to 273 plus T in degrees Celsius. Then we use this formula to convert the temperature from degrees Celsius into Kelvin. Let's consider this example here. Example number 3. Okay, it says number 1, convert 150 degrees Celsius into Kelvin. That is number 1. Number 2, convert 200 Kelvin into degrees Celsius. Number 3, a sample of gas of 0.75 cubic decimeter is at a pressure of 105 kilopascals and a temperature of 27 degrees Celsius. 3.1, if the temperature changes to 74 degrees Celsius and the pressure changes to 150 kilopascals, calculate the new volume. 3.2, if the volume of the original gas sample decreases to 190 cubic centimeter and the pressure changes to 380 kilopascals, calculate the temperature in number 1 Kelvin and number 2 in Celsius. Okay, let's do this together. Okay, this is example number 3. .1, we use this formula T equal to 273 plus T in degrees, which is 273. The temperature given there is 150 degrees. Let's punch it into our calculator quickly. How much are we getting? 273 plus 150. So we get 423 Kelvin. Okay, number 2, we're supposed now to convert 200 Kelvin into degrees Celsius. So we use the same formula, T equal to 273 plus small letter t. So if we make small letter t the subject of the formula, we have T in Kelvin minus 273, which is the same as 200 minus 273. 200 minus 273, of course, is negative 73, which is degrees Celsius. Okay. Let's consider now number 3. 3.3. Okay, let's write what is given there. We're given V1, which is the same as 0.75 cubic decimeter. Remember, cubic decimeter is the same as a liter. Then we're given also P1, which is the same as 105 kilopascals. What else is given? We're given T1, which is 27 degrees Celsius. Remember, we need to convert this T1 into Kelvin. How much are we getting? So we add 273. Then the answer here is 300 Kelvin. 300 Kelvin. So what are we supposed to calculate here? Okay, let's go to the question quickly. Okay, the first question is to calculate we need to calculate the volume, the new volume. Okay. We need to calculate the new volume. Okay, let's check which formula to use here. Which formula to use? We use the general formula P1 V1 over T1 is equal to P2 V2 over T2. Okay, what are we looking for? We're looking for V2. Let's substitute P1 is 150 kilopascals. Let's substitute the units. V1 is 0.75 cubic decimeters over T1 is 300 Kelvin. Okay, what is P2? P2 is 150 kilopascals. Okay, let's go and check again. Okay, P1 is 105. So P2 is 150. Okay. So this is 105. P2 is 150. V2 is unknown. T1 is given as 54. So we add 273. How much do we get? 327. So this is in Kelvin. Okay, so what is V2? We can now cross multiply to make V2 the subject of the formula. So we have 105 times 0.75 times 327 all over 300 times 150. Okay, let's punch to get the answer. The answer is 0.57 cubic decimeter. Okay, that is the answer. Let's quickly go back to the questions. Okay, the second question now is to calculate the temperature. If the volume of the original gas sample decreases to 190 cubic centimeter and the pressure changes to 380 kilopascals, we need to calculate now the temperature in Kelvin and also in degrees Celsius. Okay, let's check what we have now. Now V2 is equal to 190 centimeter cubed. Remember, V1 was given in cubic decimeter, which was 0.75 cubic decimeters. This is D. So which means we need to convert V2 into cubic decimeters, or we can convert cubic decimeters into centimeter cubed. So if we divide 150 by 1,000. Like to convert cubic centimeters into cubic decimeters, we divide by 1,000. So we're going to have 190 cubic centimeters divided by 1,000. Then we get our answer in cubic decimeters, which is 0.19 cubic decimeters. So you can see that the volume is decreased. Okay, let's check what else. P2, the second pressure now is changed into 380 kilopascals. Okay, let's write now the answer, 2.2.1. So we use the general formula, which is P1 V1 over T1, which is equal to P2 V2 over T2. Okay, let's make substitution there. What are we looking for? We're looking for T2 now, second temperature. Okay, let me write the formula again. P1 V1 over T1 equal to P2 V2 over T2. P1, of course, is 105 kilopascals. V1 is 0.75 cubic decimeter. And T1 is equal to 300 Kelvin. P2 is 380 kilopascals. Then V2 is 0.19 cubic decimeter all over T2, which is what we are looking for. Okay, if we cross multiply, what do we have? We have 380 kilopascals, because this T2 will come here, and everything here on top will come at the bottom, and 300 Kelvin will go there at top. Okay, so 300 will go and multiply what is on top at the other side. Then we divide by 105 kilopascals times 0.75 cubic decimeter. Okay, that is the answer there. Let's work it out quickly. How much are we getting? 275 Kelvin. Okay, that is the answer. So now we need to calculate this temperature now in degrees Celsius. That is 3.2.2. So we know that T is equal to 273 plus small letter t. So we can make T the subject of the formula, small letter t equal to capital letter T minus 273. Let's substitute T in Kelvin. We got 273 minus, okay, how much did you get there? We got 275. We got 275, then minus 273. What is the answer? Is 2. Yeah, positive. 275 is greater than 273. So it is 2 degrees Celsius. Okay, that is the answer. Okay, let's go back to the notes. All right, we are done with example number 3. Okay, let's go now to the activities. So you need to do these activities at home. Then the first activity says air is trapped in a gas tube by a column of oil. The length of the air column gives a measure of the volume of air. Pumping air into the oil reservoir can change the pressure on the air in the glass tube. The pressure is read on a pressure gauge that is calibrated in kilopascals. The results are recorded as shown in the table below. So we have the first column there, which is the volume in cubic centimeters. The second column, which is pressure in kilopascals. We are given the volumes. So PV, you need to calculate it by yourself. and also the reciprocal of pressure, which is 1 over P. You need to calculate it by yourself to complete the table here. Okay, let us consider now the questions. The first question is to give the investigative question for the Boyle's law investigation. 1.2 is to write down the hypothesis for the Boyle's law investigation. 1.3, write down the dependent, independent, and controlled variables. 1.4, you need to write down the possible apparatus for this investigation. 1.5, you need to write the method which is followed in getting the above data. 1.6, you need to complete the table by calculating the product of pressure and volume, and also by calculating the reciprocal of pressure there. 1.7, for analysis of the results given, we need to plot a graph of number 1, volume versus pressure. Number 2, the volume versus the reciprocal of the pressure. 1.7.3, by using the graph, we need to determine the relationship between the volume and pressure. 1.8, you need to write down a possible conclusion. Okay, the second activity writes as follows. A gas is enclosed in a shallow container. The temperature is adjusted and the corresponding value of volume are recorded in the table below. Okay, you can see them. The first column there is the temperature in degrees Celsius. The second column is the volume in cubic centimeters. And the third column is the temperature in Kelvin. Remember, you need to use the corresponding values there of the temperature in degrees Celsius. Okay, let's consider now the questions here quickly. The first question, 2.1. You need to name the law in the investigated, the law that is investigated above. The second question, that was supposed to be 2.2. Okay, it's fine. It's the second 2.1. Right? The investigative question of investigation. 2.2, write down the dependent, independent, and controlled variable. 2.3, write down the possible apparatus for this investigation. 2.4, for the analysis of the results given. You need to complete the column for the temperature in Kelvin. Then you need to plot a graph of volume versus temperature in degrees Celsius, and also plot a graph of volume versus temperature in kelvins. 2.5, by using the graph, determine the relationship between the volume and the temperature. Then 2.6, you need to write down a possible conclusion. Okay. Learner's activity number 3. An unknown mass of gas is sealed in a container M. The temperature is increased and the pressure inside the container is measured. The experiment is now repeated using the same mass of the same gas in a different container N. The results obtained are represented in the sketch graph below. So you can see there we have a graph of pressure versus the temperature. Okay, as you can see, X there correspond with 263. Then the pressure of 240 kilopascals correspond with 303 Kelvin. Let's consider the questions. 3.1. Determine the values of X as shown on the graph. 3.2. How does the volume of container N compare to that of container M? You need to choose from greater than, smaller than, or equal to. Then 3.3, explain the answer to question 3.2 with the aid of a relevant equation. Okay, that is the end. Please, you need to do these activities by yourself at home.